Yes, please.
Number 4, suppose you play the following game. You toss a six-sided die repeatedly until the same number comes up twice in a row, whereupon you stop. So the question asks you to draw it using 3 states. So I'm going to go ahead and draw the 3 states. And this would be the start. This is the one more state is actually going to be in the middle, and I'm going to call it D. It stands for dice. And then this is a finished state. And you have to decide what the arrows will look like. So the start state is, you can view it as your first roll of the die. And so there will be an arrow going here. And then once you're already rolling the die, you need to check to see whether the next die is the next roll is the same as the previous one. And the chance that the next roll is actually the same as the previous one is actually 1/6. And the reason it's 1/6 is because you take the roll that you had, and there's a 1/6 chance of landing that exact same roll on the next roll. And then, so the big debate right now is where the second arrow of D goes to. A common mistake was saying that the arrow goes back to S. This is actually wrong, right? Because this arrow would represent if you don't get the same face in a row. So say you roll a 6 and then you roll a 5, and then it's saying, oh, now you start the game over. But that's actually incorrect, because if you're back at S, then if you roll a 5 again after your 5, you should be at F, but there's no way to get to F from S. So really, you should be in the same situation as before if you fail. So this arrow should go back to D. And then the chance of this happening is just 1 minus 1/6, which is 5/6. And then for F, it's always just going to go back to itself, because that's usually how the finished states are defined. So there's nothing to do after that. And then now we know that since this is the only arrow going out of S, that this is 1. Okay, so that's part A. And then, is this Markov chain aperiodic? So there was a lot of confusion over this question, because maybe it wasn't as clearly defined as we would have liked it to be. But the answer is that this is actually periodic. And the reason it's periodic is because S is periodic. The definition of periodic just means that one of the states has a period, and so you just need to find one of the states with a period. And usually in an irreducible Markov chain, you only need to look at one state to decide if the entire Markov chain has a period, because if it's irreducible, then every state will have the same period. However, if you look at this is not irreducible, and then I'll explain why in part C, because that's the question. But since it's not irreducible, you sort of have to look at each state. And then, so D and F clearly have period 1. So they are aperiodic. But then notice how S cannot return to itself. So then what is the period of S? This is a tricky definitional thing. Hey CB, how do you erase a lot of text at once?
I guess you still have to use the eraser. So
okay.
Yeah, sorry.
Oh, okay, you can just highlight everything.
Yes.
Oh, okay. Okay. Let me just erase these little thingies. Okay. As to why S is periodic, the definition of periodic is there exists n greater than 1 such that the set of n such that p to the n of the state. So here I'm going to write S because that's the state you care about. non-zero, such that if this set is equal to A, like we're setting this set equal to A, then there exists, such that, so there exists an n greater than 1 such that if this set is A, then n divides everything in A. So now we have to look at what this set is equal to for n, and then what does Pn of SS mean? Pn SS is the same thing as n such that start at S and then return to S in n time steps. Because P is basically the transition matrix, so it's like if you start at S and then you do the transition n times, the probability of being at S is non-zero after transitioning n times. So therefore that's exactly what it's saying. You can return to S in n time steps. But we can see by observation that S, once you leave S, you're never going to get back to S again. Therefore this set A is equal to the empty set. Therefore any n greater than 1 divides everything in A. And this is vacuously true because there is nothing in A, so you can obviously say that anything divides everything in A. So that's why that's periodic. And then maybe C should have came before part B, but because you often use irreducibility to determine periodicity, but it didn't happen, but that's still okay. This Markov chain is actually reducible because S cannot reach S. And the definition of irreducibility is that any state can reach any state within like some number of time steps, but S cannot reach S, so that's easy to show. And does this Markov chain have a stationary distribution? Usually to find a stationary distribution, you need to solve balance equations or something like that. But for this one, you can just look at F. The stationary distribution is stat dist equals x, y, z, such that x, y, z, p is equal to x, y, z. So the x, y, z, p just means that we take a transition, and then the stationary distribution is such that after the transition, we're still in the same distribution. And then since there's a state that just goes back to itself with 100% probability, we can immediately observe that if you're already at F, you're going to stay at F forever. So that is a stationary distribution. Yeah, so I'll circle the answer. And the transition matrix for this Markov chain, the transition matrix is P such that P of ij is equal to P that, P that x of n plus 1 is equal to j, given that xn is equal to I. So I is the ith row and j is the jth column, and what that specific entry represents is the probability that you are at j on the next time step given that you are at I. So we'll start drawing the matrix. And then we can consider, okay, so first we need to identify, start, dice, and finish our states with a number, because like it doesn't really make sense to say the S entry, it has to be like the 0th entry. Okay, and then we can look at stuff of this form, P of 0, j. So what does this mean? So 0 is the I, so this would be probability that you are at j given that you are at S. Okay, so this P of 0 comma j, this is exactly the 0th row. So we can just start looking at this row right here, and we can write S's targets. Because really, this is P of 0 comma j is the probability of going to j given that you're starting at S. So it's like the arrows that are going out of S and pointing to the j's. And so we can say that this is S's targets. And then in the same way, this would be D's targets, because D is 1. And I'm 0 indexing, so this is the 0th row, this is the first row, this is the second row. F's targets. And then this would be S, D, and F. And then S has a 0% chance of going back to itself, so this is a 0. And then D would be 100%, and F is 0. And then D cannot go back to S, so that's a 0. However, it goes back to itself with 5/6 probability, as we said earlier. And then otherwise, it goes to F. And F is also pretty similar. Okay, that's the transition matrix. And then how many tosses should we expect to do before we stop? So it might be helpful to redraw the Markov chain. And then this is sort of a hitting time formula that you learn. It's the expected time of a state is equal to 1 plus the sum of probability of target times the hitting time of that target. And then it kind of makes sense because the 1 is the step you need to take, you always need to take when you transition. And then once you transition to a target with a certain probability, in that case you're at that target. So your expected number of hitting time left would be the expected hitting time for that target. And we can write the equations in a straightforward manner. So E of S would be 1 plus 1 times E of D. And then 1 is the probability of transitioning to E of D, so that's why I multiply by 1. And then, oh shoot, E of D, the screen darkened. Okay, I guess it's fine. So E of D would be 1 plus 5/6 of E of D plus 1/6 E of F. These are the two targets, but actually E of F is the target, so that would be 0, because once you're at E of F, you're automatically there. And we see that the second equation only has one variable, E of D, so we can immediately solve for E of D there. So E of D, 1/6 E of D, because subtracting 5/6 E of D from both sides is equal to 1. Therefore, E of D is equal to 6, but the actual quantity we want is E of S, and then we can get E of S just by plugging E of D in. 6 equals 7. Because E of S is the number of steps to finish the game from the beginning. So this is the final answer. Any questions? Okay.